Welcome to our presentation on the influence of finishing in Ti6Al4V AM specimens under very high cycle fatigue conditions. We'll begin by talking about the technology applied of the ultrasonic fatigue, the tested material, the experimental procedure. Afterwards, we're going to talk about the experimental results, the fatigue, and the fatigue fracture analysis, and finally the conclusions. Now in this study we have applied ultrasonic fatigue testing machines as a way to achieve the very high cycle fatigue regime. This regime occurs between 10 to the power of 6 to 10 to the power of 9 cycles. In order to reach such a high number of cycles, a piezoelectric transducer is used to excite resonance to a specific setup and the testing specimen. It's only through this testing machine that we can reach in a time reliable manner 10 to the power of 9 cycles. If we compare this to a conventional standard fatigue testing machine, to reach such high number of cycles can take easily more than 1 month, while ultrasonic fatigue testing machines can easily take less than a week. Now, the applied material to the ultrasonic fatigue testing machines is the titanium Ti6Al4V. All specimens were manufactured by the selective laser mounting method. They were manufactured in one single section vertically. Both ultrasonic specimens and basic mechanical property specimens were manufactured in the same section. No heat or hot isotactic pressing treatments of any kind were applied to the specimens after the selective laser mounting method. And here we obtained basic static mechanical properties of the titanium tested in this study. Now, as experimental procedure, all specimens were analyzed in a 3D scanner before and after polish treatment. Only half of the specimens were polished, and after the polish they were again subjected to through a 3D scanning. We also used techniques to measure the roughness before and after polish treatment, and afterwards, after the fatigue tests, all surfaces were analyzed by the same microscope. Now the polishing sequence applied to the ultrasonic specimens. We start here with the rough surface obtained by the selective laser melting. We apply different sand grade papers continuously and observe the surfaces as we sand the surface. The objective is to obtain a free damaged surface and a clean and mirror-like shaped surface. All ultrasonic fatigue test specimens were analyzed in an optical 3D scanner, as we can see in the pictures on the bottom of the slide. From those scans, we took the low deviation that selector laser melting can obtain, which was under 2% from the base dimensions. Because the specimens were analyzed before and after polishing, we quantified the removed layer of the material until mirror-like shaped surface without any defects, which resulted in between 50 to 80 micrometers in all polished specimens. Through an interferometer, we quantified the roughness from as-built to polished surface. We can see here the rough surface obtained by the selective laser method. Well, after the polishing sequence, we have a mirror-like shaped surface with very low roughness. From the interferometer results presented in the previous slide, we quantified the roughness following the ISO 4287 standard. We can clearly see that polished specimens have a much lower roughness than the as-built specimens. Now, a microstructure analysis was also conducted to the samples. Martensitic alpha titanium phase plates were obtained. This is very common to the selective laser melting method due to the rapid beam scan and cooling rate. We can also observe the square grid shaped on the microstructure. This is associated with a rotating printing direction between layers. With the polishing sequence conducted and the microstructural analysis and base static mechanical properties, the fatigue stress life experimental procedure was conducted. The stress life results show that the polished specimens proved a 30 to 40% stress life increase. Also, as-built specimens show a predominantly fatigue crack initiation at the surface. On the contrary to the as-built specimens which showed predominantly crack initiation at the surface, polished specimens proved a subsurface crack initiation in all fatigue tests. No internal crack initiation was observed in neither as-built or polished specimens. From analysis of the distance to the surface and the defect radius of the defects responsible for subsurface crack initiation, we can clearly see that closest to the surface a lower radius was presented and an overall resultant fatigue life was obtained. We can see that especially when the defects intersect the free surface, there's a considerable reduction in fatigue life. Here the specimen 6, which intersects the free surface, has a considerable lower fatigue life than predicted. Now, what type of defects are present in the SLM samples? 3 types of specimens were identified through the fracture surfaces and microstructural samples: the inner gas pores, the smooth faucets, and lax effusions. Now, a deeper analysis of the inner gas pores was conducted since it was the most recurring type of defect and was the most responsible for crack initiation at the subsurface. Now, they present a spherical shape, so they were measuring their radius, which varied between 6 to 58 micrometers, with an average of 27 micrometers between all measured pore radius. No difference in pore density from center to free surface was observed in all conducted measurements. Now, there's this important conclusion to take when observing the fatigue fracture surface in overall and comparing it to previously published results in the same titanium in SLM AM method. If we take a look at the published results in SLM titanium, tested ultrasonic frequencies, there's a continuous propagation following the same curvature until the total failure of the specimen. When we look at our specimens, it does not fully occur, where the curvature changes halfway through the propagation until the total failure. It is associated with a higher surface propagation, and this higher surface propagation we have associated residual stresses. This is also the reason why no internal crack initiation was observed in all tested specimens, only subsurface. Again, looking at an enlarged image of a fracture surface, we can see the change in curvature occurring halfway through the specimen associated with the surface propagation that is associated with the residual stresses on the surface of the specimen, which has led to only surface to subsurface crack initiation. This behavior was observed in all tested specimens, from as-built to polished specimens, where we have surface to subsurface crack initiation, a propagation following the curvature similar to the previously published results, which changes in curvature, which associated with a higher surface propagation, until the total failure of the specimen. Now, taking a deeper analysis of the fatigue fracture surface, first to as-built, we have in as-built predominantly surface crack initiation and only a single subsurface crack initiation in the pore defect. Looking first at the surface crack initiation of as-built specimens, they presented multi-crack initiation locations. For example, here the 3 different points were identified, and they all initiated from the rough surface obtained by the selective laser melting additive manufacturing process. Now, only the lowest stress amplitude specimens for as-built specimens showed a crack initiation at the subsurface. This also resulted in the highest life and in the highest number of cycles to failure specimen. Now, looking at the polished specimens, they all presented crack initiation at the subsurface defect. On the left, we have an average defect where we can observe the radius associated with the pore defect and the center distance towards the surface. On the right, we have the specimen 6, which has an interception with the free surface, which has led to a considerably lower life than predicted. Now, if we take a look at the cracking propagation at the subsurface defect, we can see the fisheye formation, which is normally associated with a very high cycle fatigue regime. In this case, we have a specimen that initiated at a smooth faucet that then had propagation in with the fine granular area. We can see here in this shape associated with the fisheye formation. Again, we have the distance to the free surface and the radius which was quantified of the smooth faucet. The taken conclusion of manufactured ultrasonic specimens by selective laser melting is that the obtained surface roughness was proved to be primarily cause of crack initiation and resultant fatigue life. When the specimens were polished, a higher life was obtained and the defects became the primary crack initiation factor. The defect size and its location showed an important role in the crack initiation and the resultant fatigue life. Now, when comparing the stress life results with previously published results in SLM titanium Ti6Al4V, we see good alignment, but no internal crack initiation and a different fracture surface shape was observed. The differences were associated with residual stresses, which were believed to be responsible for no internal crack initiation and higher surface crack initiation propagation that has led to a different fracture surface shape. These residual stresses were believed to be present since no treatment was applied, no heat treatment or hot isostatic pressure. So on behalf of the entire team, we would like to thank you for all your attention in our presentation in the influence of finishing in titanium Ti6Al4V AM specimens under very high cycle fatigue conditions.